Hey everybody, it's Ripley back again. Hope you're having a good day. We're going to cover something called the logistics curve today. Some of you have probably seen this before. Most of you have probably seen this before. And the logistics curve arises from the fact that if we remember correctly, if I take, let's say, P of t equals P naught e to the kt, and we're talking about a growth model, right? Remember, this guy comes from dp over dt equals kp. That's the differential equation from whence it comes. There's a problem. This guy grows exponentially forever. That's what it looks like, right? But we know there's a sustainability issue here. It doesn't work in true populations because eventually you outgrow your resources, and what happens is we begin to die off. So if you think about it, what's going to happen in most populations is, now if this is t and this is p of t, clearly it doesn't make a whole lot of sense to talk about negative t. So really we're starting at some initial population here, is we experience exponential growth initially, and then either predation or lack of resources or whatever carves that population back. So you end up with this S-looking curve right here. Now, this asymptotic line right here is called, hopefully you've seen it before, this is called a carrying capacity. Carrying capacity. It's basically the amount, it's the biggest the population can be within a system before resources begin to run out, or disease comes, or predation takes over, or whatever. Excuse me. Basically, it's the most P's that you can have before, or it's the most that they can get. Really, the dying off begins about here. This is when the growth rate slows down. Okay? All right, so hopefully you've seen this before. Now, we're going to end up with some notational issues here, but in our textbook, the author chooses to use capital K. All right, now remember, we've dealt with lowercase k's, and we're going to use both in this case, and it's notationally a little bit cumbersome, but don't sweat it. Okay, you'll get used to it. All right, the logistics curve, the formula for the logistics curve, you may or may not have seen, but I want to acknowledge this. Excuse me. The formula for the logistics curve is the carrying capacity divided by 1 plus AE to the negative KT. Now, let's look at this thing really quickly and see why this works really. As T gets really, really big, take a look at this thing, okay, and tell me what is going to happen to it. All right, just take a gander. What's got to happen is T gets huge. Well, what do I end up with? I end up with this thing getting huge negative. E to the huge negative is about 0, right? So this whole term turns into 0, and you end up with K over 1, which is K, which is the carrying capacity. So as time goes on, that tells us that the curve is going to head for the carrying capacity. Now, Ripley, what happens if I start above the carrying capacity? In other words, let's say you've got a meadow, and the meadow can support, I don't know, 200 deer, and we end up at time t somehow, for some, I don't know, catastrophic cataclysmic event, forces, what did I say, 500 deer? All of a sudden we got 1,000 deer in there when we start. Well, what happens then? Well, you're above the carrying capacity, right? So when I'm above the carrying capacity, whoop, I start heading for that carrying capacity again. They start dying off. Now, excuse me, this A, let me change my color here. This A, you may have seen this defined before as the carrying capacity minus the initial population divided by the initial population. Again, those of you that have done some chemistry or some biology, I want to make sure and be exhaustive as far as some of the stuff that you've seen before. Okay? Now, there is you can probably tell, right? I mean, you've got a whole family of logistics curves that we can talk about here. A whole family of them, right? So if we've got this family of solutions, then we probably started with a differential equation. Remember, all derivatives in theory are a differential equation. So any function can be defined as the solution to a differential equation if it is the antiderivative to a function, right? Or to a derivative, really. All right, so this function, this logistics curve, is defined as follows. We can define it by this differential equation, which is Kp times 1 minus P over capital K. Now keep these K's straight. K, sorry, that was terrible. All right, think about what's going on here just for a second. What are the equilibrium solutions to this? What are the equilibrium solutions? Let's talk about those. Equilibrium solutions. All right, think about that. Equilibrium solutions are where what happens? Well, it's where the derivative equals 0, right? In other words, or where we end up with a solution which is a constant. If a solution is a constant, if a function is a constant, its derivative is 0. It's real simple. So remember what we got going on here in this muddled thing, right? Our populations theoretically never are below 0. It doesn't make sense. That'd be in a time warp of some sort. So look at what's going on. Let's take a nice clean curve. It's got asymptotic behaviors to p equals 0 and to p equals capital K, right? So that would imply that our equilibrium solution should be at p equals 0 and p equals K. Well, let's see what happens. If I plug p equals 0 in, doesn't that imply automatically, since it's Kp times this, that dp over dt equals 0? Yeah, of course. Now, where's the other value? Well, just look at the curve. Where does this curve level off? What is it? Where is it asymptotic to a horizontal line? Well, at p equals K. If p equals K, this term right here goes to 1. Last I checked, 1 minus 1 is 0. 0 times anything is 0. As long as it's not infinity, remember that. And we end up with dp over dt equals 0. Now, I'm going to give you the proof. I'm going to show you how this differential equation leads to this solution. But again, very much like last section, once I've proven it to you and once we've discussed the idea that this function comes from this differential equation, use the function. Unless it asks you to prove it outright, you're going to use this as a model to prove it. But unless it asks you for that, just use the equation. There's nothing to it. Okay, so let's prove this sucker. You ready? All right, so here's the proof. And this is really all that today entails. All right, here's the proof. So dp over dt is equal to Kp times 1 minus p over capital K. Now I'm going to break one of my rules here, and you'll see here in just a sec. First things first, let's find a common denominator. It's just screaming for a common denominator. So little kp times p minus, times p times k, capital K, minus p all over capital K. All right? Everybody with me? Now, I'm going to factor out a negative because I hate negatives, and I like my coefficient of my dependent variable to be positive. So this implies that I'm going to rewrite it just because this can get out of hand pretty quickly if you're not careful. I'm going to rewrite this as negative Kp times p minus capital K over capital K. Now, here's where I'm going to break one of my rules. All right, what I'm going to do is, remember before I always said leave your constants behind, and this happens to be a constant right here. Remember my independent variable is my t, my dependent variable is my capital P, and so everything else is a constant, right? Now you might say, Ripley, why don't you leave your capital K over here because it's a constant? Well, I've done this proof 9 or 10,000 times, and I know that if I do that, it's going to make the proof a little more muddled than I want it to be, so I'm actually going to borrow it. Now, look at what we're going to do here, because this move is can screw kids up. I'm going to grab this whole section because it's got it's got dependent variables with it, and I'm going to divide it over here. I'm simply separating my variables. Okay? So watch what happens. If I divide this over here, if I divide dp by this term, I end up with capital K times dp divided by p times p minus k, right? And this equals negative k dt. All right, nothing crazy, right? And then I take the integral of both sides. Now let's just talk over here. Let me change colors so we know that these are notes. Let's talk about k over p minus, p times p minus capital K. Now hopefully you're starting to see. It gets really tricky because we got all these letters floating around, and that can get really confusing to look at. But if I did a really quick little partial fractions on this, we've done enough of this now, hopefully, between the pre-calculus and then what we did back in, 5.8, 5.9, 5.10, somewhere in there, that hopefully you're starting to see that anytime I've got a factored thing here where there's not a simple U substitution that I can do, you're going to start thinking in terms of partial fractions. So look really close. I know that my denominator of one of these things is going to be a p, and the other one's going to be p minus k, right? Now, like I said, I've done this 9,000 times, so I know that this is p minus k, and this is p. There's going to be a minus in between. Now, again, you could do this on your own if you wanted to. I know, believe it or not, that this fraction equals this fraction. I can prove it. A common denominator, or if I cross multiply, do you agree that I would get p minus quantity p minus k all over p times p minus k, right? Look close. Well, p minus, turn that into a plus, turn that into a minus, turn that into a plus. P's canceled, and I end up with k over p minus k, or over p times p minus k, excuse me. So I'm going to reset over here in black, and this integral, by using these partial fractions, these guys right here, I'm going to turn this into the integral of, remember the integral of a sum is the sum of the integrals, so this is going to be dp over p minus k, right, minus the integral of dp over p, and this guy is going to equal the integral of negative k dt. All right, well, it lost the handle. All right, so let's do this nice and slow. All right, hopefully, again, you need to start memorizing these antiderivatives just to make your life simple. If I wanted to do a u substitution to remember what dp over p minus k is, I could, but hopefully you're starting to figure out that this is the natural log of the absolute value of p minus k minus the natural log of the absolute value of p, right? And this equals what? K, negative kt, respecti negative. Now I'm going to do something a little funky here. I'm going to use my logarithm rules, because remember, at the end of the day, I'm solving for the p, and I got two p's trapped in two separate logarithms, so I'm going to do a little logarithm action here. I'm going to turn this into the natural log of p minus k over p. Remember, the difference of a logarithm is equal to the quotient, the logarithm of the quotient, okay? And this guy equals negative kt. Ooh, I got a little lazy, didn't I? When I take an antiderivative, you guys got to scream and yell at me about that. That was just straight up silly. Now, bear with me. We're doing just fine. I want to know what my p's are, right? I need, at the end of the day, I need to solve for p because it is the dependent variable, right? So I got to undo natural log. Well, how do I undo natural log? Let's change colors just because it's fun. I do e to the and e to the. And remember, hopefully you've seen this a gazillion times. This becomes p minus k over p. Remember, we discussed why those absolute values go away, right? Theoretically, p is allowed to be negative. That is okay for p to be negative given in the context of the function, of the actual function. Believe it or not, I can have values down here. All right, they end up curving like this. If p is negative, you can play with that over here. Okay, figure out why that happens. So it's not like I keep the absolute value along for the ride. The reason the absolute values are there in the first place is so that the natural log can evaluate that. I'm sure you guys are tired of dealing with that. All right, at least tired of hearing me tell you why that happens. Okay, let's look really close. E to the negative kt plus c, we've seen this a bunch. This turns into a e to the negative kt. All right, ooh, this is starting to look good. I got an a e to the negative kt over here. I'm good. Now, all I got to do is some algebra. I get p minus k equals p a e to the negative kt. All right, just simple algebra. And this implies that, what do we got here? We're going to do p minus p a e to the negative kt equals k. So all I did was subtract this guy across and add this guy over, right? Now I'm going to factor out a p and I'm going to divide through, which tells me that p of t, I can call it p of t. I know that because my dt tells me what my independent variable is. So p of t is equal to, now let's see if you can do this one, if you can see it. It's capital K, which is our carrying capacity, divided by 1 minus a e to the negative kt. Ah, crap. Well, that's, by the way, lowercase, uppercase, right?